Section 12.6 is the binomial theorem, and it has to do with the idea of taking a binomial, as we have here, a plus b, and raising it to a power. So let's take a look, let's think about what happens when we take a binomial and raise it to a power. If we have a plus b to the 0, we just remember that anything raised to the power of 0 is just 1. So I'm going to be doing there's a reason that I have it way over here, so just know that, so just 1. Now, a plus b to the power of 1, not surprising, is just a plus b. Now, when we take a plus b and we square it, we should be a little more familiar with that. I mean, we should be familiar with that. I'm going to make that a little bit smaller. And so we wouldn't be surprised to kind of be able to do that fairly fast. We will have a squared plus 2ab plus b squared. Now if we take that and we multiply it by another a plus b to get a plus b cubed, we will have an a cubed plus 3a squared b plus 3ab squared plus b cubed. Okay, now if we take that and we multiply it by another a plus b, we will have, you can probably kind of see a small bit of the pattern here, we'll have a to the 4th, we'll also have a b to the 4th at the end, and then you may kind of maybe see a little bit of what's happening where we'll have 4a cubed b plus 6. So what I want you to see that's happening here is we have a to the 4th, the next one is a cubed, and then we will have a squared. Meanwhile, we have essentially b to the 0 here, and then we have b to the power of 1, and then we'll have b squared here. And then now we have just a, so notice a to the 4th, a cubed, a squared, just a, and now we'll have b cubed. So notice b to the 0, b to the power of 1, b to the power of 2, b to the power of 3. And then the last one will be the b to the 4th. Okay, now let's take a look at just the coefficients of each term. So the pattern of the coefficients. So of course we start with 1, but I'm looking at, I don't need to write it, but you can kind of picture what these numbers are when you don't see anything. However, some of them do have coefficients that are not 1. But we're looking at the coefficients of each term here, and I'm going to put those into their own little pyramid under pattern of the coefficients. So let me get my red back here. So we have 1, and then 1, 1. Then we have 1, 2, 1. So notice doing the pyramid still. Again, I'm just using my coefficients. I have 1, 3, 3, 1, and then I have 1, 4, 6, 4, 1. And this continues on. Of course, we could raise a plus b to a higher power. This is just the beginning of what we have here. I will show you if we were to do one more of these. I could do a plus b to the 5th, but I'll focus on just showing you what would happen. I'm just going to rewrite that just due to space. So 4, 6, 4, 1. If I were to do a plus b to the 5th, we would still have 1 here. Then we'd have 5, 10, 10, 5, 1. Okay, I'm not sure if you can see the pattern yet, but if you can, this is called, I'll write this down, this is called Pascal's triangle. Pascal's triangle, that's what's happening there. Okay, so what I want you to notice is there are n plus 1 terms each row. Okay, so when we had a plus b to the 0, we had 1 term. When we had a plus b to the power of 1, we had 2 terms. So notice we have 1 more term than we do whatever the exponent is that we have here. So notice that. And as well, notice that the first term is going to be that a to the n, the last term is b to the n. So notice when we look at each term specifically, not just the Pascal's triangle of the coefficients there, notice that every time we have that first a to the n and the last is the b to the n. And then, like I already said, we're going up with 1 degree on one of the variables and we're going down on the other one. Also important is the fact that within Pascal's triangle here, there is a pattern to the coefficients. So when we look at this, I don't know how well this is going to work, but I'm trying to make myself a triangle. Making myself a triangle. What I want you to notice is that each coefficient that you see here, each number that you see here, is a sum of the two values above it. So when you see 10, it's the sum of 4 and 6. When you see this 4, it's the sum of 3 and 1. This 3 is the sum of 1 and 2. This 2 is the sum of 1 and 1. So that is where the pattern of the coefficients comes from. That's how this triangle is created. But it also is the coefficients of the terms of taking a binomial and raising it to a power. And that's kind of the interesting thing about it all. Now, to get very specific, we have a plus b to the n, and we're told that if you want to do that, so the idea here is like, how could we do this, say, without having to do a whole lot of work, without having to take a plus b times a plus b times a plus b times a plus b, 4 times or however many times. This actually gives us the way to do that. So it is a summation, it's the sum of many terms. And CK there are the coefficients, those numbers from the nth row of Pascal's triangle. Okay, so when we're asked to expand and simplify, the idea is we don't want to do that. We don't want to multiply 2x minus 3y times itself 4 times. So instead, we can follow what we have up here. We could recognize that a is 2x in this case, and b is a negative 3y. So just looking at it like this, 2x plus negative 3y to the 4th, because following the binomial theorem version 1, we need that addition sign. Then we just follow this summation. We follow this summation. Notice that it starts with k equals 0. So the idea there is that the first term that comes out of this, when k is 0, you get c sub 0 times a to the n times b to the 0. That's the first term when k equals 0. The second term is c sub 1 plus, and then we're going to have, when k is 1, it's multiplied there, give me a second, c sub 1 times a to the n minus 1, so our a is going down in degrees. Our b is going up in degrees, so it'll be b to the 1, and so on. So following this pattern, we can then find out what the multiplication is of this very quickly without having to do this whole thing out and get all these terms and combine like terms and all this stuff. So the way to think about this is the first term is going to be a to the 4th. C to the 0, so let me come back here. This is, because we're raising something to the 4th power, we want these coefficients that we have here. So 1, 4, 6, 4, 1. So 1, 4, 6, 4, 1 are going to be the coefficients of my term. So 1, then I have 4. Now the 2x is now going to be going down by 1 degree. The negative 3y, however, is making its first appearance with a degree of 1. Then we do the next 6. The next coefficient will be 6. 2x is going down by 1. Negative 3y is going up by 1 in terms of its degree. Then we have 4. Again, 2x is going down by 1, so now just 2x. Negative 3y is going up. And then our last term, coefficient of 1, is the b to the 4th, which in this case is the negative 3y to the 4th. So this is it. This is what happens when you multiply it all out, but in a more efficient fashion. Now you would want to actually come up with what these terms are. So if you want, you can pause, see if you can come up with what these terms are, and then come back, see if you got it right. So we have 2 to the 4th, which is 16. So we'll have 16x to the 4th. We have, I guess I can do a couple lines here. Let's see. Okay, so 4 times 8x cubed, and then a negative 3y, and then 6 times 4x squared times a 9y squared, and then a 4 times 2x times negative 27y cubed, and then a 81y to the 4th. And then last step would be just to multiply everything together here. So we'll have actually a negative or a minus right here. Minus, and that's going to be 96x cubed y. And then the next term we will have 216 x squared y squared, and then minus 216 xy cubed, and then our plus 81y to the 4th. So it's not that it's not any work at all, but honestly, I mean, most people would say that it's still more efficient than taking 2x minus 3y and multiplying it by itself for